Dear students, in the previous class, we have discussed how to make inference about two population means using independent samples, assuming that standard deviations from or standard deviations of both populations are equal. The procedure is known as pooled t-test. Pooled t-test requires that standard deviations are equal. Now we develop a procedure where standard deviations are not required to be equal, even though they may be. So what we consider today is how to make inferences about two population means when standard deviations are not assumed to be equal. Now, as before, we assume that population standard deviations are unknown. Population standard deviations are unknown, a usual assumption, and variable under consideration on both populations are normally distributed on both populations. Now, we begin by finding a test statistics. We begin by finding a test statistics. Now, for independent samples, the standardized version Z is equal to x bar 1 minus x bar 2 minus mu 1 minus mu 2 divided by root of sigma square 1 by n1 plus sigma square 2 by n2. The standardized version of x bar 1 minus x bar 2 that we have considered. And we know that sigma 1 square and sigma 2 square, the population variances are unknown. So, we replace these sigma 1 square and sigma 2 square with the sample counterparts. Then it becomes x bar 1 minus x bar 2 minus mu 1 minus mu 2 divided by root of s1 square by n1 plus s2 square by n2. Now this quantity can act as a test statistics because this quantity has t distribution. As we have seen, when the population variances are replaced by sample variances or population standard deviations are replaced by sample standard deviations, then Z is converted into t distribution. Now, we consider the distribution on non-pooled t statistics. The first procedure we have discussed was pooled t-test procedure. Now we consider is, as standard deviations are not assumed equal, pooling is not possible. We have what is known as non-pooled t statistics. To explain this, suppose that x is a normally distributed variable on each of two populations. For example, X is salary from private and public institutions. Then, for independent samples of size N1 and N2, independent samples of size N1 and N2 from the populations, the variable x bar 1 minus x bar 2 minus mu1 minus mu2 by root of s1 square by n1 plus s2 square by n2 follows T distribution. So this quantity, if x is normally distributed variable on both the populations with the n1 samples from the first population, n2 samples from the second population, then this quantity follows T distribution with the degrees of freedom. It is a little complicated formula. I write degrees of freedom as equal to delta is equal to S1 square by N1 plus S2 square by N2 all square divided by S1 square by N1 S1 square by N1 all square plus S2 square by N2 the whole square divided by N1 minus 1 N2 minus 1. And this formula can be calculated if you know the sample variances of population 1 and 2 and also the sample size N1 and N2. Even though its appearance is a little complicated, calculation is easy and we will not calculate it manually. We have what is known as the softwares will perform this test for us. Now, for the null hypothesis that H0 mu1 is equal to mu2, then this test statistics become x bar 1 minus x bar 2 minus 0 divided by root of s1 square by n1 plus s2 square by n2. So T with the degrees of freedom given by this equation delta. So this quantity can serve as a test statistics, and the testing procedure based on this test statistics is known as non-pooled t-test. Non-pooled t-test. The testing procedure based on this test statistics is known as non-pooled t-test. So let me write down the steps. And non-pooled t-test, as in the case of the pooled t-test, is based on three assumptions: simple random samples, independent samples, normal population or large samples. Simple random sample, independent samples, normal population or large samples. Then the steps are: step 1, formulate H0 and H1. H0 is always mu1 is equal to mu2. H1, mu1 not equal to mu2, mu1 greater than mu2, mu1 less than mu2. In the first case, it is a two-tailed test. It is a right-tailed test. It is a left-tailed test. First step. The second step is determine alpha at 5%, 1%, 10%, etc. Third step is compute t as equal to x bar 1 minus x bar 2 divided by root of s1 square by n1 plus s2 square by n2. Then the fourth step is find the critical values minus t alpha by 2 minus t alpha and t alpha in the form of a graph. It's like this: minus t alpha by 2 plus t alpha by 2 minus t alpha plus t alpha. Now, the decision rule: if the value of the t obtained from the sample is in the critical region for a right-tailed test, for a left-tailed test, for a two-tailed test at alpha level of significance, reject H0. Or if p is less than or equal to, reject alpha, again reject H0. That is the decision rule. It is a repetition of what we have discussed many times. An example given is neurosurgery operations type. Several neurosurgeons wanted to determine whether a dynamic system known as Z plate reduced operative time relative to a static system known as ALPS plate. Data is given in the book, and data is given, and the relevant quantities: dynamic system, static system. X bar 1 is equal to 394.6. X bar 2 is equal to 468.3. S1 is equal to 84.7. S2 is equal to 38.2. N1 is equal to 14. N2 is equal to 6. And as you can see, the standard deviations are considerably different, 84 and 38. So, large difference in the standard deviation between the populations suggests that pooled T is not a valid procedure. So, non-pooled T is the best procedure. Now, using the hypothesis H0, mu1 is equal to mu2, H1, mu1 is less than mu2. That is, dynamic procedure require less time than the static procedure. Degrees of freedom delta is equal to 17, alpha is equal to 0.05. T by applying the values is minus 2.681. For degrees of freedom 17 and alpha 0.05, minus T alpha by 2 is equal to minus T 0.05 is equal to minus 1.7. And P value is 0.01. So it follows that null hypothesis is rejected because the test statistics is in the critical region. So H0 is rejected and H1 is accepted, means the dynamic system requires less time, less operative time compared to static system. Now, we can also develop a pooled confidence interval procedure. So, a confidence interval of 1 minus alpha, 95% or 90% as your choice depending on alpha. Then you have T alpha by 2 and delta degrees of freedom. Then the confidence interval for given level of significance is x bar 1 minus x bar 2 plus or minus T alpha by 2 root of S1 square by En1 plus S2 square by N2. Now, in our case, a 90% confidence interval is minus 2, 25.9 using the values. So the interpretation is the dynamic system reduces operating time somewhere between 25.9 and 121.5 to 25.9, or somewhere between 25.9 and 121.5. Remember this, the interpretation of confidence intervals in the case of comparison of two means is different from the interpretation of confidence intervals in the case of a single mean. Always keep it in mind. If the end points are positive values, negative values, or a positive and negative values. So this is the non-pooled t-test procedure. If we assume that the standard deviations are different, and to see whether the standard deviations are equal or not, you just plot the normal probability plot, box plot, etc. to get insight about the distribution of two populations.